Hello, welcome to the this lecture. So previously, whatever we have covered was primarily how to design counters, right? And we also looked at two special variations of these counters, namely ring counter and a Johnson counter that was counting a very specific sequence, right? So this counter design was done using a specific kind of a flip-flop. It could be a D flip-flop or it could be a JK flip-flop, that doesn't matter. But the strategy you follow to design the counter is going to be the same. So what you always need to remember is that at any point of time, what you need to see is what is the next state, right? So at any point in time, you have a current state and you need to understand that what is the next state that is being asked, right? In a counter design, or rather than saying calling it counter, counter typically refers to a more of a sequential count where I try to do, let's say, 0, 1, 2, 3, 4, 5, 6, or I try to do a count of odd values, right? 1, 3, 5, 7, 9, and so on. This is a generalized sequence generator, right? That would be a rather correct way to express this kind of problems or a problem statement. Any kind of a sequence has to be generated. What should be the corresponding sequential circuit for that? And that sequence, if you see that what are the different number of elements that are required in the sequence, and those has to be codified in terms of, that is the state encoding, right? I'll just give one more time, quickly discuss on that. So suppose I am trying to build something called a sequence generator. Okay, so it is similar to a counter, but it's a more generic way to capture what I am trying to say, right? And this is going to be a sequence of let's say numbers or outputs, whatever you want to call them. Let's say some kind of A, then followed by B, followed by C, followed by D, followed by E, and back to A, right? This A, B, C, D, E are not consecutive numbers. That could be, they could be anything, right? A could be 7, B could be 2, C could be 3, D could be 1, and E could be 6, right? And then it's going to back to this, anything. Okay. Not only that, even this could be consuming more number of bits to individually represent that. So maybe I will tell you, kind of qualify what I am saying. This, instead of 7, I could even write 70, right? 70 followed by 20, followed by 30, followed by 10, followed by 60, right? And then back to 70. So if you ask me, based on whatever I have taught so far, 70 is going to require a large number of bits, right? So it will be 7 bits. 64 is 2 to the power 6, right? 2 to the power 5 is 32. With 5 bits, it is up to 32, 31 rather. With 6 bits, it will be 63, up to 63. But it's more than that, 70, right? You will require 7 bits. So, but 7 bits is required only to represent this number 70, but that is not necessarily a state, right? I can always say that 70 is corresponding to some state, let's say A or 1 or whatever, right? This is another state which is corresponding to 2. This is corresponding to 3. This is corresponding to 4. This is corresponding to 5. Then it becomes much more easier. It is a regular counter where 1 corresponds to the value 70, 2 corresponds to the value 20. That is simply a truth table that you can design to solve this problem, right? So this is easy. In case of the other one where I have 7, 2, 3, 1, 6, I want the state to actually roll through those values, right? As you can understand, this is a 3-bit value, 7, 2, 3, 1, 6, the state encoding. If I want to say that the state encoding themselves are 7, 2, 3, 1, 6 rather than the 70, 20, 30, they are the outputs. In this particular case, 7, 2, 3, 1, 6 are the state encodings themselves. Okay, so they have to be encoded using 3 bits. So again, going back to this table and coming back to this particular sequence, we have to look at the present state and the next state. So if your present state is 7, the next state is going to be 2. If your present state is 2, the next state is going to be 3. If it is 3, it is going to be 1. If it is 1, the next state is going to be 6. If it is 6, the next state is going to be 7. Okay, so this is something that is universally you have to do it, right? So present state and next state. And apart from that, you will have some kind of inputs. Okay, so now because the present state itself is 7, which is going to be encoded using 3 bits, you have to individually take care of those 3 bits because you will need 3 flip-flops here. Okay, that is one of the things. The other approach, right, I have also kind of expressed this thing earlier. So this is one, right, whatever I have said 7 to, you have to simply write that in terms of the state encoding. 1 1 1, if we are using 3 flip-flops, like 0 1 0, this will be 0 1 0, this will be 0 1 1, this will be 0 1 1, this will be 0 0 1, and so on, right? So instead of having 7 2 3 1 6, you have to write this Q2, Q1 and Q0, and here I have to write Q2 plus, Q1 plus, Q0 plus. These are the next states. So this is exactly what I have done here. 7 6 5 4 3 2 1, we have designed a regular down counter, but this is the same procedure that you need to follow even for this. Okay, so the other thing that I was about to mention is, as I told you in this other example here, right, what you need to do in this kind of cases is, rather than looking at the actual values, look at the number of unique states, right? So the number of unique states is going to determine the number of flip-flops. Okay, so log of that. So if you have let's say 4 states, if we don't have that 60, right, 70 20 30 10 and then back to 70, then there are 4 unique states, right? So in that case, you are just going to solve the problem using 2 flip-flops. It's a 2-bit counter. Okay, you have 5 here, so it requires 3 flip-flops. Okay, so keep this in your mind. Sometimes a sequence might be given, your state encoding might not be the sequence that themselves. Okay, but if it is, you are free to do that, right? So this is a small distinction I wanted to make, and if it is not clear, you can ask in the live sessions. That will make your confusion cleared out, right? So 70 is an output of the state, 20 is an output of the state, 30 is an output of the state, 60 is an output of the state, whereas 7 2 3 1 6 are the state themselves. Okay, anything might be required for you to be designed, right? So depending on that, you have to take the judgment call. Okay, so we have looked into this problem, and current state and the next state, of course, depending on the value of the next state, or what is the value of the previous state, what is the value of the next state, you have to look at the excitation table and derive the next state logic. So the next state logic can either be based on a D flip-flop, or it could be a JK flip-flop, it could be a T flip-flop, but the process is the same. Just look at the excitation level, look at the transition, and fill in the values of the corresponding inputs of that particular flip-flop. For JK, there are 2 inputs, J and K. For D and T, there are only 1 input, D or T. Okay. So we looked into the design of this counter in details. I think I made a quick revision and then also gave you some additional perspectives. Then we looked into these 2 kinds of special counters. One was the ring counter, and the ring counter went through this kind of a state machine where each one output, right, is only one output is on. The rest of the outputs are all off, and that kind of shifts over time, right? It shifts to the right hand side. So if you have 4 of these outputs, or the 4 LEDs, let's say, at one point of time the LED is going to glow, and then at the next state, one on the right hand side of that is going to glow, and so on, right? And once it reaches the extreme end, or the least significant bit, if we call the rightmost LED as the least significant bit, it is going to roll over to the extreme left, which is the most significant bit, and this is going to continue, right? So it's more like a LED chaser kind of a thing. It's keeping on chasing the LED, right? The LED keeps on moving and again going back. So it forms like a ring structure. Also, the implementation has a feedback from the extreme right hand side flip flop to the extreme left hand side flip flop, which looks like a ring. Okay. This one was an important comment. So this is called one hot encoded. This has many applications in various areas of processor design or in general in computer hardware, where only one bit is up, the rest of the bits are all off. It's called one hot encoding. So this was the architecture of the design. As you can see that this is the one that goes back directly, right? And this is why it is called a ring counter. It has a ring structure. Okay, this is the ring structure, this red colored ring. Then we looked at the video, right? You are also encouraged to try out this kind of things, right? So in circuit verse, I told you to do some of these designs. So please make sure that you indeed try things out. Okay. So once I preset the circuit, it is going to create. So as you can see that only one of them is up, the rest of the outputs are all off. That's why you see this staircase kind of a pattern. Okay. Okay. Then we looked into this Johnson counter, and this Johnson counter exactly looks like this. And you have, if you have an n-bit Johnson counter, the length of the sequence that it is going to show is 2n. It is very easy to verify that. And the counting sequence, as I told you earlier, was a gray code sequence, right? So only one bit is changing at a particular point in time. So if I'm making a transition from state I to state I minus 1 or state I plus 1, both of them are going to differ from state I in terms of only a single bit, only one bit. Okay. So this is kind of important, and this can be used. It has many different applications why gray code might be used. For you, you have used gray code in the K maps, right? So in that case, it was required for doing this vanishing. The x and x complement should be close to each other and they could be circled off. So this was the Johnson counter. The last but not the least was this BCD counter, which is also kind of an important and very useful circuit. And this is primarily for counting decimal numbers, right? Because for most of the circuits that you see in the real world, like a digital watch or a microwave oven or your induction stove, right? Everything is going to have a front panel that shows these numbers, right? What is the temperature, how long you want to run the microwave oven for, washing machine, right? They will always have this decimal display, AC, air conditioning, right? So BCD stands for binary coded decimal, where we take these 4 bits, right? And instead of having these 4 bits go from 0 to 0000 to 1111, right? We actually go from 0000 to 1001, which is nothing but 9, right? So it actually goes from 0 to 9. Everything after that, right? So let's say 10, 1010 to 15, 1111. So A to F, right? These are ignored. Okay, because they will become hexadecimal representations. We do not have any hexadecimal representation because we are talking about a decimal system. So in the decimal system, we are only going to roll from 0 to 9. After that, it has to become 0, right? So this has a lot of use cases, right? Wherever you see counters in the real world, most of them will be a BCD counter wherever you are interfacing with human beings. Okay. So it is basically a mod 10 counter. So whenever the count is 10, it is going to revert back to 0. So 10 is not going to be shown, or which is hexadecimal A. Okay, and you can stitch these counters together, right? So once you have the units placed, let's say as a VCD counter, it counts from 0 to 9. Next time it goes to 0, the next bit could actually be incremented to 1. So you can stack along these counters and create numbers with higher number of digits. Okay, so this is one example where I have already shown you a 2-digit number, right? So it's a number, it's a counter that is going to count from 0 to 99. Okay, and I have already discussed this, so I'm not going to repeat how exactly it is working. It will take some amount of time for discussing how this 9 is being compared, right? And after 9, it is enabling the second one, right? So 0, 0 to 0, 9. After that, when this 9 is changing from 9 to 0, this is also going to increment this one, right? So after 0, 9, it is going to become 1, 0. After 1, 9, it is going to become 2, 0, right? So that part is actually captured by this flag. Whenever there is this 9 happening, this is going to automatically enable this particular counter, which is going to increment the count by 1. Okay, so and you can also do a 3-digit number and so on. You can try it out, and it is very easy to verify. You can create a circuit like this and verify this in Circuitverse, right? Circuitverse has this LED segment, 7-segment LED segments, drivers, where you can give the 3-digit, 4-digit, 4-bit number, and you can ask it to show the corresponding hexadecimal pattern. It will show. So it is very easy to verify your design. So you can, as an exercise, what you can try to do, you can create a 3-digit counter, right? 3-digit BCD counter that is going to count from 000 to 999. Okay, only decimal values, mind it. So I have shown you this example where I am doing 00 to 99. You should try out 000 to 999. Okay. Okay, so now there is one more application using these flip-flops, primarily targeted towards storage, which is called a register, right? Typically, what this we are using this D flip-flops till now was to design sequential circuits, primarily to make some kind of device with systems like counters and so on. There are many other applications, frequency dividers, that I have not discussed, right? Given the focus of the class is a little bit larger, or even the overall course is little bit larger, so I'm not going to go into very minute details of the various things that could be done using the flip-flops, but we are primarily covering two things in details. One is the counter design, the other one is the fact that these registers, which could be made using D flip-flops and could be used for storing data. Okay, so what is a register? The register is nothing but a collection of flip-flops, and every flip-flop, as you know, has the capability to hold a bit. Okay, so we can use D latches to store more data, right? How can you use more D latches to store more data? You basically use more D latches, right? You need more, right? So currently, whatever I have taught earlier, this is a gated D latch. Whatever you write in D, and if you have the write enable on, is going to be reflected in Q. Okay, and if your write enable is off and the system is powered, Q is going to be held, right? Whatever be the value of D, it doesn't matter. Q is going to be saved. Okay, so every such unit is going to save 1 bit. Okay, if we use more D latches, like the way I have shown in the figure, it is going to hold more number of bits, right? So instead of using or storing a single bit, you can start storing a binary number, right? Suppose it's a 4-bit binary number, Q0, Q1, Q2, Q3, whatever be the most significant, least significant is up to you, how you define it. But this is going to be a collection of 4 bits, and each bit is being held by a individual D flip-flop. Okay, so if you want to do write this 4 bits simultaneously, then you have to enable them together. So in that case, all the write enables are going to be together, tied together. Okay, so this is how exactly I meant. So as you can see, this is so this was dangling, this was dangling, and this was dangling. But if I want to treat Q0 through Q3, instead of treating them as individual bits, if I am trying to treat them as a 4-bit number, then I have to have this write enable done simultaneously, because D0 to D3 are going to be changed simultaneously, suppose, and Q0 and Q2, Q3 are going to be also be changed simultaneously whenever there is a clock pulse, and I make the write enable 1, right? So this is the concept of a register. So the register is going to hold a binary number, and the size of the binary number is typically the size of the register. Okay, the size of the binary number could be 8 bits, it could be 4 bits, right? Typically 8 bits registers are commonly available. So you will have this 8 bits to be stored, right? And you can read from the register, you can write to the register, and you can have this write enable on. If the write enable is on, you can basically trying to write to the register. If your write enable is off, you can have a potential, you can read from the register. Okay, so note that you have to also provide the clock pulse, right? Typically you are dealing with synchronous sequential circuit, so multiple registers will be clocked to build a bigger system and so on. But in this particular example, the usage of clock is not apparent. But when you make a system that has many registers together, and registers need to talk to each other, in those situations this kind of facility will be required, because we just don't want to store the data in a given register then be done, right? What is necessary is also to read from the register and put the data somewhere else, right? So there could be 2 registers or 3 registers, and this register should support inter-register data transfer. Okay, for those kind of reasons, we might have to use some clock signals or some kind of a synchronization across the different registers. Okay, so now let us come back to the definition one more time and just get some of the definitions clarified. So here we have a register or a structure that stores more than 1 bit and can be read from and written to. The register holds 4 bits and this data is referenced by Q3 to 0. So as if it's an array. So there are 4 bits in the register. That is how we can refer the register, the different bits of the register. So if I say Q just 2, that means that means 1 bit, right? One particular bit, Q2 bit. Okay. Otherwise, it is referenced as Q3 to 0. So there are 4 entities, 4 bits. So often we will use this as this cross sign. If you see, this is typically called a bus, and this 4 means it's a 4-bit bus. Okay. Similarly, this is also a 4-bit bus. This is a 4-bit input bus. This is a 4-bit output bus. Okay, and this is your write enable. So if you are allowing data to be written from the input bus to the register, you have to do this write enable. You can also read. So these concepts are going to come up later. I am going to talk about it. How can you read? How can you stop reading, and so on. Maybe towards the later part, right? Maybe on when you start talking about computer design, we will talk about it a little bit in more details, right? How these registers could be individually interfaced. Okay, so this is about the register. There's nothing complicated. Now we will be using this register as a memory device. So there will be many such binary numbers that are to be stored, right? And we need to retrieve those binary numbers or store binary numbers and so on. So we need to have some other extra mechanism, particularly something called addressing, to access this memory device, right? And this memory device, you can think for now in a simplistic way, is a collection of such registers. Okay, so memory is comprised of locations that can be written or read from. An example memory with 4 locations. Suppose we have only 4 locations in the memory. They are going to have addresses. There will be 4 addresses, right? And these 4 addresses could be expressed using the number of bits will be log of the number of locations. So in case we have 4 locations, we can definitely assign them the address 0001 1011, right? It's something that you already know. If you have 3 bits, you can support up to 8 memory locations. If you have 10 bits, you can support up to 1024 locations, right? 2 to the power 10. Okay. So this is very important that every unique location in the memory is indexed with a unique address. Okay. So 4 locations are going to require 2 address bits. The other thing is a very important term is called the addressability. Okay. How much data you are addressing per location, right? If you go to an address, let's say some address 00 or 01, or let's say for a 3-bit memory addressing scheme, if you want to go to another location called 110, and you look up what is stored there, right? The number of bits of information stored in each location is called the addressability. Okay. So you will always come up with this kind of terminology is called byte addressable memory, right? What is a byte addressable memory? Byte addressable memory is doesn't matter how many bytes are stored. There could be 1 million bytes, but if you go to a particular memory location, you will have only 1 byte. You cannot refer to individual bits within that byte. Okay. So if I draw a picture, I think it might become a little bit more clear. This is called the size of the memory. Okay. Size of the memory. Okay. So the memory is going to consist of multiple such memory wards, right? Every location you are going to have something. Okay. So there is some number of bits. So I can call them B number of bits. But how many locations are there, right? What is the size of the memory? In this particular case, if you are going to have a 10-bit address, you are going to have, let's say for a 10-bit address, okay, the number of locations, the number of unique locations is going to become 2 to the power 10, which is equal to 1024. Okay. Right. So you have 1024 different unique pockets that are addressable. You can reach to that. But if you want to, let's say, address, say, half of these bits that are stored here, not the entire thing, that is not possible. Okay. Because once you go to a particular pocket, you have to either read it or not read it in its entirety. Okay. So if you go to this particular location, this entire thing has to be read by you. And this is what is called the addressability. So the addressability has to be, say, there are 8 bits. So you can directly address 8 bits together. Okay, you cannot address 4 bits here. You cannot address 1 bit here. Okay, so there's a trade-off. How much you want to address at a time. Suppose if you want to address individual bits, right, then of course the address size is going to become much more, right? Sometimes it is not practical. So there is always a trade-off that whether I want to address, let's say, 4 bits at a time, 8 bits or 32 bits at a time, right? So in that case, the number of times we are going to issue the address will also decrease, right? Suppose instead of 8, my size of each particular memory location is 32, let's say. In that case, by one memory lookup, I am going to load 32 bits in my for computation, let's say, right? So that is the definition of addressability, but there is a trade-off. How much, what kind of addressability we are going to have, whether it is a byte, it's a short, it's 32 bits, right? It could be anything. Okay. the entire set of unique locations in the memory is called the address space. So here I have already told you that the number of unique locations in this particular case is 2 to the power 10 or 1024. That's the address space, 1 kilo. So if your memory, this particular memory is byte addressable, the total size is going to be 1 kilobyte. Okay, because there are 10-bit addresses and every address is like, the memory is byte addressable. Okay, so if you have a 32-bit addressability, 4-byte addressability, in that case it will become 4 kilobyte. Okay, because at every location you are going to have 4 bytes and totally there are 1 kilo locations, so it becomes 4 kilobytes. So yeah, typical memory will be much larger. It will have maybe billions of locations, like huge, so gigabytes and so on. Okay. So for an implementing a very simple memory array, we will have, let's say, 3-bit addressability. So 3 bits are going to be stored at a particular memory location, and the address space size is going to be 2, right? So address space size 2 means there are only 2 possible locations, right? One location, the first location is going to have 3 bits, the other location is going to have 3 bits. Totally we will store 6 bits, but we cannot refer to 6 bits individually. Either I have to refer to the first chunk of 3 bits or the next chunk of 3 bits. So this is one particular bit, right? That is how it is stored, right? And we are going to have something like this. There is an address space is of size 2. So 1 bit is enough for the address. Either it is the top or the bottom, right? If it is address is 0, we refer to the top row. If the address is 1, we refer to the bottom row. And for every row, we are having a collection of 3 bits. That is the addressability. You cannot look up bit 1 or bit 0. You have to look up bit 2, bit 1, bit 0 together. Okay. So this is a 6-bit memory array with 3-bit addressability, and the address space is of size 2.